we have observed, based on a strain amplitude driven experiment, we've observed a relation between the plastic and elastic components of the strain versus number of cycles to failure. Individually on a log-log scale, they seem to fit on a line, and therefore we fit them on a line explicitly individually. One part of it is already in the Basquin form implicitly or indirectly. The other part is new to us, and it was proposed in the 1950s, and it seems to be a representative behavior. But now let us move to the final goal and combine these two pieces of the puzzle and relate the strain amplitude to number of cycles to failure. So let's remember these two plots associated with plastic strain and the elastic strain amplitude. So red is plastic, blue is elastic. And let's proceed and put everything on the same figure and generate the total strain versus life curve. So we might as well just say strain versus life curve, but just to emphasize that this is different from plastic or elastic strain amplitude, I'm going to call it total strain versus life curve. So we have, again, the on a log-log scale. Okay, that's the convention in the case of strain-based fatigue. On a log-log scale, we have number of cycles to failure versus now the total strain amplitude. That total strain could range from 10 to the minus 4 to 10 to the minus 2 and even larger values. And the number of cycles to failure, 10 to the 1, 100, 1000, 10 to the 4. Certainly we cannot say that this high cycle fatigue, a portion of it is certainly a low cycle fatigue. And then we had generated two models. We saw that, first of all, the plastic strain seemed to fit on a line that looked like this. So this is associated with epsilon PA. On the other hand, the elastic strain also followed a straight line here with a smaller slope, it turns out. That was our observation essentially. And let's say that is the curve that we have for the elastic portion of the strain. Now, we remember that the total strain, epsilon A, is equal to the sum of the plastic and the elastic contributions to the strain amplitude. All right. So if we sum them and draw the corresponding line, so first of all, when the life is very small, we notice that the plastic strains are very large. Okay, so we are observing essentially that when the life is very small, plasticity is much more significant compared to elasticity, so red is above blue, whereas if number of cycles is increasing to failure, and we see that that is accompanied by smaller plastic strains compared to elastic strains. So in order to achieve large life, we need to make sure that plastic strains are small, and in order to, if we induce very large stresses, they are accompanied by very large plastic strains compared to elastic strains, and we end up with small strains. So if we sum these things to, because we're on a log scale and PA is much larger than EA, then we will get a sum that is going to be much closer to the red line on the log scale. Whereas if we're here, because we're on the log scale again, these values are of an order of, maybe one order of magnitude larger than these values. So I'm going to be closer to the blue line. So I will start off close to the red line and end up close to the blue line. So that essentially is the idea. So this here is the total strain curve versus life. Okay, so given the total strain, now I can map it to number of cycles to failure. And now, emphatically, that curve is not a line. It has a certain curvature. And on the other hand, I know that individually I had lines, and now I can make use of this equality and simply write, well, the total strain has a plastic contribution, which we called epsilon prime f 2nf to the power c. So this part is the plastic strain plus the elastic contribution, sigma f prime over e 2nf to the power b. And now this allows us to have a final relation between the total strain amplitude and number of cycles to failure. Okay, so this is what we were aiming at. This is a strain-based approach to fatigue, and it is called, right, so given epsilon a, now we are able to predict number of cycles to failure, and this is called the Coffin-Manson equation. Okay. So in the stress-based approach, we're given the stress amplitude, go for number of cycles to failure through the Baskin equation. In the strain-based approach, we're given the strain amplitude, and we go for the number of cycles to failure through the Coffin-Manson equation. All right. And so when you look at this equation, you see, first of all, that we have 4 constants for data fit. Which are sigma f prime, b, epsilon prime f, and c. And again I highlight, because these 4 constants for a given strain amplitude, I will end up relating, if you like, the green line to the number of cycles to failure and use these constants to do that fit. These are going to be constants that I need to determine newly for this range of cycles, which is, in this case, for instance, predominantly low cycles. So these are not necessarily those of high cycle. Now, it turns out that sometimes they are. Okay, just means that the stress-based approach also works in low cycle regime for those isolated, or let's say for those instances. But in general, we want to regard as sigma f prime and b, although we gave them the same notation as in the Baskin equation, we want to regard them as independent fitting parameters. Now, having said all of that, of course, we need to also realize something significant about the strain-based approach, about Coffin-Manson equation, namely its generality. And in some sense, notice that if we were able to determine these constants not over a small range of cycles that is predominantly in the low cycle regime, if we were able to collect data over a broader range that moves into the high cycle regime, if I were to make this data fit in that regime, then notice that in that regime, as I proceed further and further into higher cycles, what we see is that we have essentially the total strain being almost only elastic. In other words, the plastic portion is going to 0, so this portion is going to be omitted, and we end up with a relation. If I multiply E with epsilon A, that's going to be the alternating stress, we end up with the Baskin form, which suggests that the Baskin form is already implicit. I know it's implicit in there, but also practically it is applicable in high cycle regime as well. But it naturally emerges from the strain-based approach, and I don't have to separately invoke it. So the Baskin equation, if you like, is a special case of Coffin-Manson equation. From that perspective, Coffin-Manson equation is more general. It is able to also incorporate significant effect of the plastic strain on the number of cycles to failure. Right? So now there is one more remark that we would like to make regarding low cycle versus high cycle. Now you see that there is a very particular point here where the elastic and plastic strain amplitudes are going to be of the same value. Okay, there is a certain life at which the total strain has equal plastic and elastic contributions. Let's call that NT. Okay, and NT is referred to as the transition fatigue life. We can of course easily calculate it because I know that epsilon PA is equal to this quantity here, epsilon prime F, 2NF to the power C. And on the other hand, if epsilon PA is supposed to be equal to epsilon EA, which it is at that point, right, then epsilon EA is equal to that portion of the model, sigma F prime over E 2NF to the power B. So the transition fatigue life is defined as the life at which the elastic and plastic strain amplitudes are the same. By setting that equality here, we can now extract the value of NT. So NF is equal to NT if this equality is invoked, and from that the transition fatigue life can be extracted to be 1 over 2 sigma F prime over E epsilon F prime to the power 1 C minus B. And the transition fatigue life essentially serves the purpose of clarifying that fuzzy transition between low to high cycle fatigue. Now, the transition ultimately will still be fuzzy actually, but at least we now know the region around which then that transition is probably going to take place. So NT could be, first of all, or number of NF, let's say, number of cycles to failure could be much less than NT. If that is the case, we are over here. In that case, if NF is much less than NT, we see that red is much higher than blue on the log scale. That's a significant difference. So in this case, plastic strains are dominating. So plasticity dominates. Now, on the other hand, if NF is much larger than NT, in other words, if I'm here, red is very small, blue is much higher, this is where elasticity dominates. So one says, therefore, that if we are in this region, in other words, if NF is much less than NT, so we are going towards low cycle fatigue, or if elasticity dominates, in other words, if NF is larger than NT, then we're talking about high cycle fatigue. Okay, because high cycle fatigue, the motivation was, we stated it, it turns out, and now that motivation is implicitly appearing here. If we want to go up to relatively high cycles, plasticity has to be negligible, because we observe that high cycles are associated with small plasticity, and that's what, and we end up with the Basquin equation, which is the stress-based approach, and hence we already had stated with that in mind that the Basquin, the stress-based approach, is for high cycle fatigue where there is little or no plasticity. And that's what we are now seeing here. But where does that transition occur? We see now that there is a number NT, the transition fatigue life, that helps us quantify that, because above a certain value, plasticity is negligible, elasticity starts to dominate, and we have high cycle fatigue and low cycle in the other direction. But still, the transition is still fuzzy, okay? Because certainly here plasticity dominates, certainly here elasticity dominates, but here in this region it's not very clear. But at least we now have a number that probably depends on the material, depends on the application, but we now know that, for instance, there might be cases where 10 to the 5 cycles is actually not a very high number of cycles because perhaps there are still significant plasticity effects. So NF might be, 10 to the 5 might be larger than NT, but perhaps not large enough, so there are still plasticity effects there, or vice versa. So we have now a number, sorry, this is not NF ultimately, it's NT, material dependent relation, so let's say to NT. NT is a number that is material dependent, and depending on that value, in relation to that value, we can look at the value of NF and determine whether we are towards the low or high cycle regime. So now we don't have to say 10 to the 2 to 10 to the 4 for that fuzzy transition. We actually have a number with respect to, we can judge an order of magnitude or less. We can set a boundary. And that value will depend on the material. So if we summarize now, we've stated a strain-based approach, and we've stated that it is valid in a broad range of number of cycles to failure, provided that the material, free material constants, the parameters of the data fit are determined from data points that lie on a broad range. But the focus usually with the strain-based approach is on a small number of cycles, where you focus on small number of cycles to failure and collect data from there, use it to determine these constants, and the goal is you measure the strain amplitude and determine number of cycles to failure.